In this video, we are going to have the proof of second isomorphism theorem and the third isomorphism theorem. So first, second isomorphism theorem, it states that let G be a group with H and of course N also has subgroups, and N is normal in G. Of the two, H is just a subgroup and N is normal in G. Then H intersection N is normal in H. It is normal in H, and Hn mod N is isomorphic to H mod H intersection N. So what is given? We write let a G be a group with H and N as subgroups and N to be normal in G. Then H intersection N is normal in H. So this we have given in the solved problem 2 in section 2.6. So we have H intersection N to be normal in H, and therefore this exists as a group. And similarly, N, if you consider, since N is normal in G and Hn is a subgroup of G, for this we can refer solved problem 9 in section 2.6. So using that, we have N to be normal in Hn. It is normal in G, but this one is a subgroup of G, so we can very well say that N is normal in Hn also. NH will be same as Hn, so that is what we would have established in that problem. So we have N to be normal in Hn also. So this one also exists as a group. So there is a point in discussing or whether such a thing that we can discuss or not, because structure should be maintained for homomorphism. Otherwise, if we don't have structure, then we cannot talk about the homomorphism at all, because it is structure preserving mapping. Now we define sigma from H to Hn mod N by, to prove this we make use of first isomorphism theorem. We make use of the first isomorphism theorem or fundamental theorem on homomorphism. So the idea is this, that is, you establish an onto homomorphism between these two with kernel H intersection N. Then by first isomorphism theorem, you have, because H2 Hn mod N, you have onto homomorphism, say this is onto homomorphism. Then in that case, you can have, if you have the kernel to be H intersection N, if you have the kernel to be H intersection N, then H mod H intersection N will be isomorphic to, this will be isomorphic to your Hn mod N. So that is the idea. So we'll consider the mapping, the rule being defined in this way. It is well defined because that is how it is defined. Once I consider H, you have this left coset. See, actually, if you consider G mod N, in that we have the elements either left coset representation or right coset representation that we can have. If we follow left coset representation, this is how we write Gn, where G range over capital G. So this is the representation of any element in G mod N. So likewise, if we consider Hn mod N, we can have it as small, because that this G should be in G. So likewise here, whatever I write to the left of N, that should be from Hn. But we know that any element in Hn is of the form small h, small n. So where small h range over capital H and small n range over capital N. But because our small n belongs to capital N, this Nn will be in capital N only. Nn will be equal to N whenever N is a member of capital N, small n is a member of, small n is a member of capital N, means this Nn will be equal to N. So you have this to be like this, Hn, where H range over capital H, that alone, H range over capital H. So we are justified in writing this rule in this way. Sigma of H is Hn for every H in the domain. Now, so the way in which sigma is defined, it is obviously well defined as well as onto. So that's very obvious. and we have to show that it's a homomorphism. And then once we show that it's a homomorphism, only then we can talk about the kernel. So kernel will we will establish that to be H intersection n. So to prove homomorphism, this is what we have. Sigma of HH prime is HH prime n. That's by the definition of the mapping. And because n is normal in G, we have n is normal in G, we have this one being rewritten as Hn, H prime n, but this is nothing but the image of H and sigma. This is nothing but image of H prime under sigma. So sigma of HH prime is sigma of H into sigma of H prime, and therefore your sigma is a homomorphism. Because it's a homomorphism, we talk about the kernel. So that is all those elements of the domain which are mapped onto the identity element of the codomain. The identity element of the codomain is n. But sigma of H is defined in this way. So you have this. So whenever Hn equals n, no other go, you'll have to have your H to be in n. So it is all those H in H for which your H is in n. So H is present in H as well as in capital N. So you have kernel sigma to be H intersection n. So by the first isomorphism theorem or fundamental theorem on homomorphism, we have Hn mod n to be isomorphic to H mod H intersection n. So since sigma from H to Hn mod n is an onto homomorphism with kernel this H intersection n, by first isomorphism theorem we have this. So that proves the second isomorphism theorem. Now coming to third isomorphism theorem, we are given that phi to be a homomorphism of G onto G bar with kernel K. And we are given n bar to be a normal subgroup of G bar. So in one of the lemmas, we have shown that whenever n bar is normal in G bar and phi is a mapping which is onto homomorphism from G to G bar, then corresponding to this n bar, n which is defined in this way will be normal subgroup in G. So G mod n will exist as a group, and because n bar is normal in G bar, G bar mod n bar will also exist as a group. So this is meaningful. And once we prove that n by k or n mod k is normal in G mod k, even G mod k mod n mod k will also exist as a quotient group. So this is existing as a quotient group, and this also will exist as a quotient group. So the statement, can we discuss such a, can we give such a statement? Yes. So we will establish it, but the structure, do we have them or not? So that is what is discussed now. Now for the first part, to show that G mod n is isomorphic to G bar mod n bar, we proceed like this. What is given? First we'll write, let phi be a homomorphism of G onto G bar with kernel K, let n bar be a normal subgroup of G bar and n be this. Then n is normal, that should be written. Then n is normal in G. Then n is normal in G. That has to be written. Then you can define this is normal in G. So that's a borrowed result from the previous lemma. In one of the subdivisions we have established that. So that is borrowed here. So now you define sigma from G to G bar mod n bar by sigma of G is n bar phi of G. So here we have considered the right coset representation. So either right or left coset that we can consider. So there is nothing wrong. But in the same we cannot consider both. That is both left or right representation. Either left coset representation we'll have to use in the same discussion. And what we had in the previous theorem was left coset. That was in the previous theorem. But once we consider this, we'll have to have this representation. So this sigma is defined in this way. Now because the way in which it is defined, it's obvious that sigma is well defined, and because your phi is homomorphism and n bar is normal, and phi is a homomorphism. So because of these two only, we have our sigma to be a homomorphism. Now, because sigma is a homomorphism, we can consider the kernel of it, all those elements in G, whose image under sigma is the identity element, that is n bar here. So we have written that, and this is n bar, phi of G is n bar. So it is again HA equals H means we'll have to have, this is true in both ways. So A must belong to H. So phi of G should be there in n bar. But all those G in G for which phi of G belongs to n bar is nothing but n. That is by this one. We could have named, we have named this as 1. So we have kernel sigma to be n. Now we have sigma from G to G bar mod n bar to be an onto homomorphism with kernel n. Therefore, by first isomorphism theorem, we have this G mod n isomorphic to G bar mod n bar. Now to prove this one, that G mod n is isomorphic to this, we first prove the following claim. In this claim, what we show is n mod k is normal in G mod k. So for which we'll have to consider an element in G mod k, take it as kg, and an element in n mod k, take it as kn. We'll have to consider kg, kn, kg inverse. Because k is normal in G, you can have, so you know that k is normal in G, then product of two right coset is again a right coset. So that is used here. So you have k, g and g inverse, and this is member of n, and so you can say that this is why it's a member of n, because your small n here, small n is a member of capital N, and here your small g is a member of capital G, and capital N is normal in G. So we conclude that G and G inverse is in N. So this is in N. So you can write this as a member of n mod k. So what is required that we have got? So n mod k is normal in G mod k. Now we prove this. So for that we shall consider psi to be, see, we are going to have two methods to prove this. In the first one, we are going to define a mapping psi from G mod k to G mod n in this way. Any element here will be kg, and any element with the help of this g, we are going to have the right hand side element, that representation. So you have ng. So this is defined for every kg in G mod k. Then it can be easily seen that this psi is well defined. Psi is onto, that's obvious, and it's also a homomorphism, and kernel is n mod k. So why do we say that the kernel is n mod k? See, proving that it's a homomorphism psi goes like this. You will have to consider two elements, say kg and kg prime. This is nothing but psi of kgg prime, because k is a normal subgroup, and this is nothing but ngg prime, because n is normal. We have ng prime. And this is nothing but psi of kg into psi of kg prime. So you have psi to be a homomorphism. And on to, that's very obvious. So we need to have the existence of G alone, that is assured here. So we can have kg to be the pre-image. And so now we have, so psi being a homomorphism, kernel psi we can find. It is all those elements in G mod k. So that is kg in G mod k, for which you have psi of kg to be the identity element of the codomain, which is n. So it is all those kg in G mod k, for which psi of kg, what is psi of kg? It is ng. So ng is equal to n. So all those kg, capital K it is, for which ng equals n. So this implies that my G belongs to n. So this collection can only be n by k, that is n mod k. So we have psi is an onto homomorphism with kernel n mod k. Therefore, by first isomorphism theorem, G mod k mod n mod k is isomorphic to G mod n. So this is one way of proving it. If we make use of the first part of it, then we can also give the proof in the following way. Since phi is a homomorphism of G onto G bar with kernel K, by first isomorphism theorem, we have G mod K to be isomorphic to G bar. So we are going to take that isomorphism as theta. So how that could be defined, Kg taken to phi of G. So theta of Kg equals phi of G. So this theta can be defined in this way to have what is required, that is G mod K isomorphic to G bar. Now for this we'll consider the kernel. Kernel theta is all those elements in the domain which are mapped onto the identity element of the codomain. So you have this. But theta of Kg is phi of G. So Kg belongs to G mod K, Kg, and the next step we have the same thing to be all those Kg in G mod K, for which phi of G n bar is n bar. Now E bar being a member of n bar, we have phi of G to be in n bar. So because phi of G is in n bar, we can have this step. Because phi of G is in n bar, we have this step. So this in turn gives phi of G to be in n bar. Okay, so this in turn gives phi of G to be in n bar, or even directly also E bar belongs to n bar, so directly also you can conclude. So Kg, so kernel theta is all those right cosets Kg for which phi of G is in n bar. But this is nothing but n mod K. Why? Because phi of G is in n bar. If we have this, then our G should be there in n. G should be there in n. So when we consider this Kg, we'll have to have Kg. Here G is a member of capital G. But now that we have got, whenever phi of G is in n bar, where will that G be? By the definition of n. It should be there in n. So we can very well conclude, instead of this as G mod K, now that G being a member of n, we can have this correction to be n mod K. So since theta from G mod K to G bar is an onto homomorphism with kernel n mod K, so by 1, that is the first subdivision, what we just now proved, we have to have this to be true. And here we notice that this kernel theta, see, if we have to make use of the previous one, the condition required is you need to have phi from G to G bar to be an onto homomorphism with kernel K. Then G mod n only is isomorphic to G bar. So there what is known was this K is contained in n. K is contained in n. But in this case we have of course theta from G mod K to G bar. This we have, and here kernel theta itself is n mod K. It is not that like in the previous case kernel contained in that n that we had. Here kernel theta itself is n mod K. So you have the condition required to make use of the first subdivision to be true. So we have to have G mod K to be G mod K mod n mod K to be isomorphic to G bar mod n bar. Again we make use of the first one because there we have said that G mod n is isomorphic to G bar mod n bar. So by transitivity, we know that whenever A is isomorphic to A, B, C are subgroups, I mean groups means A isomorphic to B, B isomorphic to C means A isomorphic to C. So we make use of that. So using that we have G mod n to be isomorphic to G mod K mod n mod K. So that proves the second part of it. And with that the third isomorphism theorem proof ends. Thank you.